Welcome to the deep dive. Today, we're headed to the tropics, but don't worry, you can keep your snow boots on. We're exploring the world of crop modeling, specifically the history of SARRA. That's Système d'analyse régionale des risques agroclimatiques in French.
Yeah, that's right. And what's really fascinating is we're getting a sneak peek at a publication. It's about the history of SARRA. It's going to be published soon, and it's written in French. So we thought it would be cool to kind of break it all down for our English-speaking audience.
Exactly. So picture this. You're a farmer in the tropics. You're dealing with unpredictable rainfall. Sometimes it's crazy hot, and you're constantly needing to adapt to a changing environment. How can science help you navigate all of this? That's where SARRA comes in.
You got it. These crop models are kind of like crystal balls.
Yeah.
But instead of giving these vague predictions, they offer data-driven insights into how the climate might impact your crops and how you can kind of adapt your practices to get the best yields possible. It's especially important for regions where data might be scarce.
So we're talking about decades of research and innovation, starting with something as basic as just analyzing rainfall and evolving into these incredibly sophisticated simulations that can model entire agricultural landscapes.
It's a pretty incredible journey. It all began back in the 1960s with organizations like Orstom. You might know them as IRD today, and IRAT. They were really focused on understanding rainfall patterns in the tropics.
I love a good origin story.
Yeah.
But how did analyzing rainfall lead to the creation of actual crop models?
It was the foundation, you know. They started developing these early water balance models. They didn't even have names at first. These models were really basic, but they were fundamental to understanding how the amount of water impacts crop growth.
And did these early models actually get used out in the real world?
Oh, absolutely. In Brazil, one of these early unnamed models was used to develop something called agroclimate zoning for rain-fed rice. It was a groundbreaking development. It helped guide decisions on what to plant and where to plant it based on rainfall patterns.
Wow, that's amazing. So even these super early models had a real impact. What happened next?
Well, as you can imagine, the models became more sophisticated over time. In the 1980s, the BIP-BEEP IRAT model was developed. This model calculated water balance over a decade, so a 10-year period. And it was designed to focus on staple crops that were vital in many tropical regions, like millet, sorghum, maize, and groundnuts.
That makes a lot of sense, focusing on the crops that are really important. Where was this model used?
Mostly in Francophone West Africa. It was a great tool for all sorts of agroclimate studies, and also for monitoring agricultural campaigns as they were taking place, helping to make sure farmers had the best chance of success given the weather.
Okay, so we've gone from basic rainfall analysis to a model that can look at water availability over a decade. That's quite an evolution. But I have a feeling this is only the beginning of the SARRA story.
You're right, things are about to get even more interesting. Remember that devastating drought in the Sahel region in 1973? That's what led to the creation of CILSS, an organization that's dedicated to combating drought in the region.
Right, CILSS. They're a major player in the Sahel. So how does SARRA fit into all of this?
Well, through a partnership between SARRA and AgriMet. AgriMet is a specialized institution within CLS. They work together to create a regional early warning system. They were really determined to prevent those kinds of catastrophic droughts from happening again. Think about this. They had over 700 rain gauge stations in 9 different countries, all feeding data into the system designed to predict and mitigate drought risks.
700 rain gauge stations. That's a massive amount of data collection. So how did the crop models come into play here?
Okay, so there was this model called DHC4. It was actually based on BIP4, and it played a key role in this early warning system. DHC stands for Diagnostic Hydrological 2. It's essentially a tool to diagnose the water status of crops.
So DHC4 could tell you if your crops were stressed because they weren't getting enough water.
Exactly. It was a really important indicator for agricultural planning. Like, it could help you figure out the optimal time to plant millet and even get an idea of your expected yield. And what made DHC4 so powerful was its ability to interface directly with AgioMet's climate and rainfall databases.
So they could run simulations for tons of different locations and update their forecasts quickly throughout the growing season.
Yeah, exactly. That meant that they could get this timely information to the people who needed it most, like farmers and policymakers. DHC4 really did have a big impact on operational monitoring and managing food crises in the Sahel. It even helped build capacity within national meteorological services by empowering them to analyze and interpret their own data.
Now that's what I call a win-win.
Yo.
So we've seen these models go from basic rainfall analysis to these sophisticated tools for predicting droughts and guiding agricultural decisions.
Yeah.
Where do we go from here?
Well, remember how we were talking about the PC revolution earlier? The arrival of personal computers in the 1990s opened up so many new possibilities for crop modeling.
Yes, the dawn of the PC.
I bet that changed everything.
Oh, it did. Suddenly, users had all these new demands. They wanted forecasting capabilities. They wanted a model that could adapt to all these different cropping systems, and they wanted it to be user-friendly. Basically, they wanted a model that could do it all. And that's where SARRA makes its grand entrance. Tell me about this game changer.
The first version of SARRA was launched in 1991. It wasn't just one program, it was a suite of 3 independent software programs. SARRAMET, SARRAVIL, and SARRAZON. Each module had its own special function.
So it was like a Swiss Army knife of crop modeling.
Yeah. That's a good way to put it. SARRAMET was all about managing and analyzing climate data, while SARRAVIL focused on calculations at the plot level, like figuring out the water balance for a specific field. Then there was SARRAZON, which was designed to assess the water balance for entire networks of rain gauges.
Wow, that's impressive. What were some of the other things that set SARRA apart from those earlier models?
Well, unlike DHC4, which was really focused on millet, SARRA was designed to be multi-species, so you could use it to simulate the growth of all sorts of different crops, which made it much more versatile. And it could also simulate the water dynamics daily, giving researchers a much more detailed picture than those earlier models could provide.
Daily simulations. That's getting pretty granular. How did SARRA stack up against some of the other crop models out there at that time?
There were some really complex models out there like Series DSAT and APSIM, but those relied on having tons of data for yield estimations. SARRA took a different approach. It was all about finding that balance between complexity and accessibility.
Makes sense. Especially in areas where resources are limited, you need a model that's easy to use and doesn't need mountains of data.
Exactly. And that's a big reason why SARRA caught on so quickly. It was used all across sub-Saharan Africa, Brazil, and Indonesia. In Brazil, they even integrated it into a tool called SARRA.
SARRA. What's that?
It stands for Zoneamento Agrícola de Risco Climático, which translates to agricultural risk zoning. It's a system that's used for agricultural risk zoning and insurance. Think of it this way. ZRC could help you figure out the risk of a crop failing because of drought or other climate-related factors, and SARRA played a big part in making that possible.
Wow. So we've gone from rainfall analysis to drought prediction to a model that's helping shape agricultural insurance policies. The evolution of SARRA is pretty amazing.
And it doesn't stop there. As researchers started using SARRA more and more, they realized it could be even better. They started seeing limitations in how it represented these really complex plant processes, especially when it came to how plants respond to water stress. And that leads us to the next chapter in the SARRA story, SARRA H.
Bring it on. I'm ready for the next level of crop modeling.
Well, before we get into that, I'm curious, what stood out to you so far about the development of SARRA?
Honestly, I'm really impressed by how adaptable it is. From those early days of just analyzing rainfall with pen and paper to software that's actually shaping agricultural policies. It's really remarkable how science responds to the needs of the real world. Plus, I love that a crop model can have such a dramatic origin story. A drought in the Sahel.
It really shows that research never happens in a vacuum. These advancements are driven by partnerships, collaborations, and a desire to solve real-world problems. But like you said, the story continues. As we entered the 21st century, climate change became a major focus for agricultural research. It was no longer just this looming threat, it was a reality that needed to be addressed.
And did SARRA rise to the challenge?
It did. That's where SARRA H comes in. We were starting to get all these climate change projections from those global climate models, the GCMs, and they were producing massive amounts of data. To really study the impact of these projections on crops, researchers needed a model that could handle these huge simulations and do it efficiently.
So they needed a model that could crunch all those numbers without breaking a sweat. Was SARRA H the answer?
It was released in 2001. SARRA H was a more complex version built on a modular platform. It could now simulate both daily carbon and water balances, taking into account things like water availability and radiation, which can really stress a plant out.
Hold on, carbon balance. That's new. Why was that added?
Adding the carbon balance meant that researchers could go beyond just looking at water stress. Now, SARRA H could simulate the growth of different parts of the plant, the roots, stems, leaves, and even the grain. It could track how biomass accumulated over time, taking into account both the carbon and water dynamics.
So it wasn't just telling you if a plant was stressed, but how it was stressed and even what parts were being affected.
You got it. It could also simulate leaf area index, or LAI. Think of LAI as a measure of how much leaf area a plant has compared to the ground it covers. Imagine you're looking down at a field from above. LAI tells you how much of that ground is covered by leaves. More leaves means the plant can capture more sunlight, which can lead to higher yields.
I'm starting to see how those extra layers of complexity really give SARRA H a much deeper understanding of how plants actually grow.
And there's more. They also integrated processes to account for something called photoperiodism. That's how a plant responds to the length of day and night, which can affect things like flowering and ultimately yield. This was especially important for those traditional sorghum varieties in the Sahel.
So not only was SARRA H more sophisticated when it came to simulating plant physiology, but it was also considering the genetic makeup of different varieties. It's pretty amazing.
It is, and to make sure they were on the right track, they rigorously validated the model using field observations. This showed that SARRA H was really good at representing yield variability across different environments. So now not only could the model tell you how much a crop might yield, but also how that yield could vary from year to year based on the weather.
That kind of information is so valuable for farmers and policymakers.
Absolutely. So SARRA H was a major step forward in terms of its complexity and ability to simulate all those intricate plant processes. But was this the final form of SARRA?
The answer to that is no. We were just talking about the PC revolution.
Mm-hmm.
But by the 2010s, there was another technological revolution in full swing. Advancements in Earth observation and geomatics, satellites, drones, all this spatial data is all becoming more accessible.
And that brings us to another turning point in the story of SARRA. Think about it. We now had access to this high-resolution satellite imagery, particularly from the European Sentinel program. This meant researchers could actually see what was happening on the ground in amazing detail. They could track changes in vegetation over time, monitor crop health, and even estimate yields from space.
So could they take all this incredible satellite data and incorporate it into SARRA?
That's exactly what they did. They adapted SARRA H to run on a platform called Ocelot. It's designed to work with georeferenced objects. This meant they could go beyond just simulating crop growth at a single point and start looking at how it varied across whole landscapes.
So instead of just looking at a single field, they could zoom out and see what was happening across a whole region.
Precisely. And that's how SARRA was born. It's a fully spatialized version of SARRA capable of doing grid-based calculations. They could take those high-resolution satellite images, combine them with climate data, and simulate crop growth across vast areas.
That's an incredible leap. From simulating a single plot of land to mapping out entire agricultural landscapes. What kind of impact did this have?
It completely changed how organizations like AGR-WIMET approached agricultural monitoring and risk management. SARRA could generate these thematic maps. Think of them as maps with a specific theme or focus. They could show things like planting dates, the stage of crop development, and even potential yield estimates. And all of this was visualized across the whole landscape. This information was incredibly valuable. Governments, NGOs, National Meteorological Services, they could get a much clearer picture of what was happening on the ground and make more informed decisions.
It's incredible how this one family of models, SARRA, has evolved to incorporate all these advancements in science and technology. From rainfall analysis to satellite imagery, it's like a timeline of innovation in agricultural research.
It really is, and it speaks to the power of collaboration and this constant drive to improve.
So we have SARRA H, which sounds like an amazing research tool, and we have SARRA O, this spatial powerhouse for large-scale analysis. What are the key differences between these two versions today?
Well, SARRA H is mostly used as a desktop application. For research diagnostic sensitivity analyses and training, it's really user-friendly, pretty easy to calibrate, and it gives you those really clear graphical outputs. It's the go-to model. If you want to really dig deep and understand how different factors influence crop growth in a specific location.
And what about SARRA O? How's that being used these days?
SARRA O is a multi-platform software. It's written in Java. It's what you would use for those large-scale routine simulations that cover big areas. It uses climate data in the form of daily geotiff files, so it can take into account things like how rainfall and temperature vary across the landscape.
So SARRA H is your trusty lab partner, while SARRA O is the workhorse for doing that regional scale analysis.
I like that analogy. Both versions have their strength, and they're still being used and refined today.
Okay, so we've covered a lot of ground here, from the very beginning of SARRA to its current forms. Before we wrap up this incredible journey, I'm curious, what do you think makes the SARRA family of models so unique?
What's always impressed me? It's their simplicity and robustness. They really get at the core of how rainfall and cropping calendars influence crop growth, in these tropical environments. And they do it with a relatively small number of parameters, which makes them super accessible, especially in regions where data is limited and resources are scarce.
That's something we've seen throughout this whole deep dive. this focus on making the knowledge useful and accessible. It's not just science for the sake of science. It's science with a purpose.
Exactly. And I think that's a big part of why SARRA has had such success. It was designed as a tool for a very specific purpose. And it's continued to evolve to meet the changing needs of the people who actually use it.
But like any model, it's got to have its limitations, right?
Of course. One of the big ones is that SARRA doesn't directly consider soil nutrient deficits. It mainly focuses on water availability, which is great for keeping the model simple and easy to use, but it doesn't capture the full complexity of how soil fertility can impact crop growth.
So it's a trade-off between simplicity and capturing every little detail of the system. Are there other limitations to keep in mind?
Well, with SARRA, because it's spatial, the quality and relevance of the input data are super important. Think about it. If you're using soil maps to figure out water holding capacity and those maps aren't accurate, your simulations are going to be off too.
It's the classic garbage in, garbage out problem.
Exactly. And even just choosing which satellite data to use for rainfall estimates can really affect your results. So spatialization definitely opens up a ton of possibilities, but it also comes with new challenges.
Okay, so we've talked about the incredible history of SARRA, its origins, its evolution, its strengths, and its limitations. It sounds like this story isn't over yet.
Yeah.
What do you see as the future for SARRA?
Oh, I think the future of SARRA is really bright. To stay relevant and keep making a difference, it needs to keep evolving. Imagine a future where SARRA can simulate even more species and varieties, capturing the incredible diversity of crops that are grown in the tropics.
That would be amazing. But wouldn't that make the model more complex? We were just talking about how important it is to keep it simple and accessible.
Yeah, it's a balancing act for sure. The key is to expand its capabilities without losing those core values. That's why open sourcing the code is so important. If more researchers can get access to the code and contribute to developing it, that will ensure that SARRA stays adaptable and keeps being relevant. There's already a GitHub repository for it.
Ah, the power of open source. Love it. It's like having a global team of experts working together to make SARRA the best it can be.
That's a great way to put it. And as technology keeps advancing, SARRA needs to keep up too. Imagine incorporating even more spatial data from satellites and other sources. That would allow for even more precise simulations and give us a much deeper understanding of how crop growth changes across different landscapes.
Even more spatial data. Sounds like SARRA might need a bigger hard drive.
It might. But think about the possibilities. We could simulate the effects of specific agricultural practices, like using cover crops or different tillage methods, and actually see how those impact yields and water use. That would be amazing for promoting more sustainable agriculture.
Now that's what I call actionable information. It's been fascinating to see how SARRA has evolved, from simple rainfall analysis to a tool that can help us create more sustainable and resilient farming systems. It really highlights the power of scientific research and innovation.
It really does. And it also shows just how crucial these models are for building agricultural systems that can handle the challenges of climate change and ensure food security for everyone.
So as we wrap up our deep dive into the world of SARRA, is there one thought-provoking question you want to leave with our listeners?
Here's something to think about. Given that SARRA can simulate all these different cropping systems and climate scenarios, how can we use these models to create better agricultural policies and practices in a way that benefits both people and the planet? It's a complex issue. It's going to take collaboration, innovation, and a willingness to use data to make decisions.
What a great question to end on. Thanks for joining us on this journey through the history of SARRA. Until next time, keep exploring, keep learning, and keep diving deep.